So we saw that the functional perspective on the beta function. So let's make a very small recap. Here we compute beta functions, quantum field theories. Quantum field theories of the very basic form. Our goal is to find the fixed point of the renormalization group, which, when the theory is Euclidean and equilibrium, it's almost certainly it's a conformal field theory. So it's a way to find out all candidate quantum conformal field theory, which then maybe you attack with a bootstrap. But if you do not know which are the symmetries, when there are multi-component, you don't know. The possibility is huge. So we saw that the other week, the first week was devoted to the theory, let's say, of this approach. We saw that when you do calculation working with, at the functional level, where you don't specify the potential, then you compute beta functionals, and everything is much more simple. Okay? But even more importantly, when now you go to the multi-component case, there is no additional new computations. Because, for example, and also we have seen that the upper critical dimension in the one component case labels one-to-one the universality classes. So when I say the critical 4, which means that I'm doing dimensional organization in 4 minus epsilon, I'm actually doing the Ising universality class. Okay, so the beta functional, in this case, let me eliminate the 4 pi's that I can always redefine away. They have no physical content. Is this simple expression. Okay. So this is leading order and next to leading order. And then you have a beta zeta, which is minus 1 over 6, 4. This is all the information that you have in the Epsilon-Expansion. Every beta function that you compute in every textbook, whatever, is already contained inside this information. And actually the only 2 coefficients that you need to compute are these 2, these 3. Okay? And in many cases, you can use a different theory. You don't need to use 5 to the 4, but you need to normalize it here, and you can have shortcuts. You can have tricks. And so you highlight which one is the fundamental information, and you find the simplest way. But now what is really important is that now, if now we go to n greater than 1, so for example, I want to do the ON model, I don't have to do nothing new, because there is only one way to transform this expression when I have a 2-index object, and it's just this one. So here I have V. I have one V, A, B, C, one V, and then we have V. So this is basically this type of connection. So we can write A, B, C. And here we have, this one will go in one of these points. Okay, so we have A, B, C. So this one goes this one. So this can put A, this can be in B. And this can be in C, this can be in D, this is in C, and this is in D. Okay, so this is the only way in which you can upgrade to the multi-component case of beta functional. And for the other one, you will have 2 external indices, and it will be minus 1 of this, and then I have A, B, C, I, A, B, C, J. Okay? So you can look at the combinatorics, you can think about it, but what is really important is that now these numbers are the same. So the RG numbers are independent of the group structure. So this means, first of all, that whenever you study the UN model in any textbook, in any application, and you do the calculation all over again, you're just redoing the same calculation over and over. This is very important for us because it's the basis of what we're going to do today. Because now, not only we can do this for the upper critical dimension 4, but we can do this for all the possible upper critical dimensions. And the fact that is that higher order upper critical dimensions, other upper critical dimensions have the leading order contribution, which is a higher orders in the loops. And this idea of upgrading things works in all of them. So without work, we get the general beta functional, which are our master functionals, for example, the critical 3, And you see these expressions are to be highly non-trivial. And actually, while this is a 2-loop contribution, these 4 terms are equivalent to a 4-loop contributions. And also this one is a 4-loop contribution. So we can climb the ladder of contributions. And this is the tetracritical. And you see that also here, this is like 3-loop, and these terms are equivalent of 6-loop contribution. And now you have it for any imaginable theory with continuous or discrete symmetry. And then we have also, for example, because we're going to show you an application of this today, which is the 5/2, which is equivalent to a 8 loops computation, which will be unimaginable. You will never attempt to do something like this, even for the UN model like we do today, because it's a huge amount of calculations. But since we were exploiting the fact that in one component, the expression is simple, and we can derive some general formulas, and then these general formulas, we can dress them with the indices, we completely avoid this task without never computing a loop. But now having at disposal the most general beta function for n components for any hypercritical dimension. And as you remember from the other lectures, we have that if this is 2, 3, 4, 5, and 6, there are, this is 6, then there is this, there are some specific hypercritical dimension, and most of them are rational, where the theory is mean field, and you expect the CFT to exist in all the range below it. So if you work with 6, 4, and this is the 10/3 that was overlooked, there was another output of our work, there are new candidate hypercritical dimensions that then you combine with new symmetries and explore systematically all 3-dimensional conformal field theories. Clearly in the Epsilon-Expansion, okay? So then there is, when there are multi-component, there is still the option that the theory becomes first order before it reaches 3. So it's not a 1-to-1 correspondence for the multi-component, but you have the basin of possible candidates, and then you can study them. And then also these are the candidates to be the Landau-Ginzburg-Lagrangian for CFTs in 2D, which you only know as minimal models or rational conformal field theories. And then, okay, these are the things. So we started, now let's apply this to the ON models. And here, already last time I showed you how to apply it to the standard case. And so you go from this formula, so now you go from this formula to this formula. So you see in 3 steps, we arrive to this non-trivial G equation, which is a functional equation. So it's a differential equation for the potential, and the potential runs according to this structure. So it's not only one coupling that runs, but the whole family of coupling combined in the potential. Already here there is a branching point, because for many questions, if you want to go beyond perturbation theory, you need to solve the full partial differential equation that tells you the full evolution of the potential. But for the moment, we are interested in looking at fixed points, and since in fixed points in dimensional regularization there is only one coupling, there is no loss of information in projecting this equation just to the marginal coupling. And if we want to compute the basic critical exponents, to the marginal coupling plus the mass. So I choose this form of the potential, right? And
basically you always assume that the potential is at 0 and the fields are not 0. You never assume that.
No, in this case, since we are just projecting out, so this is just a way to find the beta function.
Right, but somehow the starting point from the beta function is always the origin.
Yeah, but you can also expand, make an expansion. If you are in a broken phase, right, you can expand around the minima, and actually, and define, because at the end, what are the beta functions? The beta functions are a Taylor expansion of the potential around a certain point. So I can do the Taylor expansion around 0, okay, and this defines the mass and so on, or I can decide to do it around my rho star. And this defines another set of coupling, another parameterization of theory space, which could be more efficient. Actually, this is a big field, let's say technical subfield when you do functional normalization. Finding the right, because with this, with the functional equation, you can do something that you cannot do in perturbation theory. Because in perturbation theory, you're forced, when you compute beta function, to compute it here. Now we can compute beta function around here. But even more, the lesson is that if you try to solve the full thing, you gain even more information. And actually, you can also write this thing for large field, so make an expansion at infinity, and solve this equation in a more general way. There are a lot of things that it's not the main purpose of what I'm doing today in these days, but it's some of the things where the functional approach is very useful. Okay, so now let me see. So now I just want to show you some that it is actually very simple to obtain information to compute high order beta functions. So since we also had some, so here I prepared some examples for today, because today we're going to do two applications of these master formulas, which are two new applications that I did. One is to study multi-critical ON models, which somehow are the n-component spherical symmetry generalization of the multi-critical models. And since this model, due to the Marmin-Wegner theorem, do not exist in 2 dimensions because they have continuous symmetry, what is interesting in their physics is their large n limit. And so today we're going to compute the large n limit of their critical exponents. And we will see that there are some surprises, because the large n limit of some of them is non-trivial. And so the ON phase space for large n, when you have higher multi-criticality, is completely non-trivial and still to be understood. So there are still open questions in field theory that you expect to know everything. So let me see now how we can transfer, how I actually do then some of the computation that I do. So in particular, this is Xtensor, no? It's an add-on for Mathematica that you can download for free, and it's very nice, and it's very comfortable when you do computation involving tensor, because what we want to do now is to, all the job here, okay, here I did by hand the ON case. You can write projectors, you can decompose the equation, you can do some analytical manipulation to go from the general formula to the beta function, which are this one here. It's nice to do it one time, but then when you do it with the serious stuff, it's billions of pages of algebra, so you cannot do it by hand. So what we want to do is able to write this equation in Mathematica, decide the form of the potential, and run it everything and get it as an output the distillato, so just the beta functions. So I normally do this with MathTensor. And so here, so you install it. You make some definition to make some manipulation, and then, okay, here I have now the 3 critical case. So this was the standard case that we did by hand. So now what is new? Now I want to do, and in the standard case, let me just review before we do. So we get the beta function for the mass and for the critical coupling, and the anomalous dimension, okay, by doing the contraction. Now, we are in the case where we have only just one invariant, so the fixed point is trivial. You can do it analytically, okay, this is the ON fixed points. And then what you do the stability matrix, what we did, or you just expand the beta functions around their critical value, and you know that the scaling and the eigenvalues of the RG are related to critical exponent. Then the ON theory can be deformed both with ON symmetric perturbation and ON asymmetric anisotropic. We're not gonna go inside that, we're gonna just look at the 3 typical exponents, which are eta, u, and omega. And so this are their expressions, okay? Clearly we reproduce the Ising case. Now, what we noticed already, and what was known since ever, is that the large n limit of the theory is trivial. So somebody expected, okay, clear, you go to the large n and you go to the Gaussian theory. In particular, you reproduce the spherical model. And so, okay, what do you expect non-trivial? To be non-trivial in... then this thing here is related to self-avoiding random walk, and this limit is a discussion we already made last time. So one expects, okay, nothing new can come out from an ON theory. Well, let's have a look at, now that we have the full power of these master formulas, let's look at the 3 critical case. So this is the beta functional, this is the leading order, and then this is the leading order, and then we have the next leading order, which I didn't copy again, which is this second part here. This is the leading order, and then there is the second part, and this is the anomalous dimension functional. So if we just transform the leading order, is this term here. This is already 2-loop information, but then we will have critical 4-loop information. So now we decide the form of the potential, the mass and a coupling, lambda. And now we want to obtain the beta function. So this is just the, this step is the only step that now every time we just have to do. Do the algebra that brings you from that to, so now how to do that? We do that with this program. Let's see if all the packages are installed. So here I define, do you see enough? Let me go to 100, 125, even 150. So here I just, you see, this is the metric which I define it to be a flat manifold, so it's just the delta, and it's represented as a delta. When A and B are like this, they are an upper index. When they have a minus sign, they are a lower index. Then I define 2 vectors, okay, which are the n component representations. And so you see this is the representation of this contraction. And then here I just wrote down explicitly in terms of the field, not in terms of the row, this thing. So you can see, for example, that then I have, there are values, I can use the command contract metric. This command will contract this, and so we'll take, for example, let me just show you some, if you, Control G, this is if I do, where is it? Wait. If I do contract metric here, you see, no, wait. This will just do this kind of manipulation. It's quite obvious. So do you know this package already? Do you use it?
No, I usually don't.
Okay, in any case, it's if you want to do manipulations with tensor, this is very useful way to implement it in Mathematica. So then, for example, you see here when I do this command, what happens is that then I define the rule in my definition, and this rule is basically the one that goes from the variables to the raw variables. And so you see that this is exactly the form of the potential that we have, that we want to plug inside, is this expression here. So now what I do, what I want to do is to find the vertices, okay? Because I need to find Vij, Vijk, and so on, and I need to find them. So I need to use these formulas all the way to, so with V3, then I need clearly V2, I need V5 here, and I think I need, yes, even a V5. So I need to obtain these vertices in an automatic way. So to do that, I do this trick. I basically use another definition. In this definition, I replace the field with the field plus epsilon perturbation field, and then I will collect coefficients of a certain order in epsilon. And so now this object here, when I strip out the perturbation, you see this is the 2 vertex, so it has 2 perturbations. This one has 3 perturbation. This one has 4 perturbations. When I strip away the perturbation, this is exactly Vijk once it is symmetrized. Okay, so you see I copy this part here, and I define in this part here the 2 vertex. I put it here, I symmetrize it, and this defines my V2 of E and F. Okay, so this is my V, and then I do the same thing here. And I contract some of the raw to make it the cleanest possible I can. Then this is my V4, and this is my V5. Okay, and then I have even V6, which I need for the anomalous dimension. So you see, okay, so these are the vertices of the ON model. Now, so slow. Okay, so these are the vertices. Now that I've done this, I just need to go and do just type in the expression. So here, this is the leading order, which is just this thing here, okay? I've just, you can always redefine the field eliminating the 4 pi's, so we always do that. So we have only the non-trivial part of the coefficient, which is 1/3. So put it here, and this is the outcome, okay? So this is the contribution that comes from the leading order part. Which is you see the contribution is only to lambda, to rho to the third power. Because on the left-hand side of this, we have the sum of the beta, we have the derivative. So what we are doing here is we have that the derivative with respect to the RG scale of u is equal to 1/3 Vijk written in terms of the raw variables. So this thing here is, as we wrote our vertex, this thing is the derivative of this part here. So it's the beta function of m squared times rho plus 1/6 the beta function of lambda times rho cube is equal to this expression evaluated in that. So now we see that this expression at leading order is just 2/3 22 plus 3n. Okay, this is the dimension of the manifold for us, the dimension of lambda square rho. So what we want to do here is to actually write rho cube. I want to write 1/6 rho cube. So I will take away this, and then I will have to put a 4 here. Okay? So now you see that this part here, this is the invariant, which is this part here. So I know that beta lambda is equal to, and here, 4/22 plus 3n lambda squared. This is the leading order contribution. And so we have computed the beta function at leading order. And then clearly this is the dimensionful beta function. Then we have to introduce the dimensionless beta function. And this, I will, here I'm sloppy, I use the same letter for the dimensionful and the dimensionless, but there is the anomalous dimension and the epsilon in the middle. So this will add this term here. So you see this is the leading order contribution, and is the one that we have just computed now. Now we just go on. So this is leading order. Next to leading order, this is, we are now doing the equivalent of, so this is two loop information. So if you do it with Feynman diagrams, this is already L equal 2. So it's not really something you do in 5 minutes. You have to, but now we do 4 loops information. And now we have 4 terms. Because you see, now if you go back here, I go to my master formula. See, I have 1/6, this combination, minus 4/3, this combination, and then minus pi square over 12, this combination. So this is the 1/6. And so I go here, few seconds, and it does. And this is the output.
The term which does not scale with n.
Yes.
Where did it come out from contracting? The 22.
See, here is all compressed. We can see it from this. Let's go.
I think from Feynman diagram it should come from counterterms, right?
It could be, yes, because but now there are no counterterms in this step because this is the leading order. It's only the next to leading order that gets counterterms. But you see from this, we're not doing this. We're doing this. Sorry. So you see that here there is this is the beta functional. So you can look at from here. So normally there is the radial component and the other component, no? Because this is the one which survives when n is equal to 1. So this is the easing part, and this is the other mode, the n minus 1 other modes. And so n here is explicitly only here. So you see that this, what comes out from these things, this is quadratic. So yeah, one can try to trace it if he needs it. So then we do the other contribution, and okay, in a few seconds you get the contribution, which is this one. So you see that here we have, first of all, this is a raw term, so this renormalizes the mass, while the second term here renormalizes, this one renormalizes the mass, and in fact is proportional to the mass. And this is the next to leading contribution to the renormalization of the coupling. And then we compute the third part, which is a little bit more involved, but there's no problem, it comes out. And then the anomalous dimension, okay, which is immediate. So now we have all the information. So, and this code is general, it applies to any theory. So now the anomalous dimension is equal to just this expression, okay, because beta z evaluated in 0 is equal to minus eta, the identity. Okay, so beta ij, delta ij. So you trace and you have a factor of n. So eta is equal to minus 1 over n beta z evaluated at 0 field. So h was our beta z, and since our potential was of order 6, h was already 6 derivatives, so it was already independent of the field. So we just need to divide by 1 over the dimension, which is n. So we get the closure expression for the anomalous dimension, which is this one. And then simply we write down the beta of the mass. So there is the classical scaling dimension, and then there are the leading order, okay, which is B0, and the free next to leading order, of which we take the coefficient of the term rho. Okay, exactly like we said there. We take the coefficient of the term rho on this side, and this is the beta function. And so this is the final result for the beta function. And then we do the same, okay? And then this is the full beta function for the ON case. And this is the result that I write here. So in this way, we have straightforwardly computed the renormalization group flow for the tricritical ON model. And this is a non-trivial dependence on n, which is the meaty part. So now the fixed point is trivial. Okay, it's again dimensional regularization. There is only one invariant, so there is no algebraic problem to find the fixed point, and we just set the mass goes to 0 from here, and then we just need to solve. This is clearly this is the leading correction, then there is other correction to the fixed point, which are not used. We don't need them for the critical exponents. How to compute the critical exponents in the usual way. So you have the fixed point. So we solve this one, okay, which is what we wrote before. So this is the fixed point. This is the value of the fixed point. Clearly, it matches the one of the tricritical. So this is the anomalous dimension evaluated, and this is the anomalous dimension of the tricriticalized model. So the second minimal unitary minimal model has upper critical dimension 3, and there this is its anomalous dimension, and then we have all the generalization. So these are all new critical new. Now, what is interesting, and then how do I compute the critical exponent nu? I just do the stability matrix, as you know, and then I collect the eigenvalue and I evaluate them at the fixed point, and then you know that the negative one, the minus the inverse of the negative one, is the anomalous, is the eta, the nu, which is then this expression here. Okay. And so this gives us this expression. Clearly, I can study the whole spectrum. I can study any kind of perturbation. But now we're just interested to understand which fixed point is this, and if there is a non-trivial large n limit. So we just focus on the two first critical exponent and see what happens. Okay, first of all, notice that there is a difference between the standard one model and the multi-critical version. Is that in the standard one, nu has a contribution which is proportional to epsilon. Okay, is this one, which is present, while the multi-critical ones, you need to go to next to leading order to find non-trivial information. And this is related to the fact that we have seen before that this, which is the first contribution to the beta function of the mass, comes at 2 loops. No, comes at 4 loops in this case, and next to leading order. So it's easing, it's somehow peculiar. Easing has the peculiarity that you get a non-trivial contribution to the beta function of the mass already at the leading order, which in that case is also 1 loop. Here the leading order is 2 loop, but you don't get a contribution, because a leading order we found only contribution to the coupling. So you have to go to the next to leading order. So this means that the critical exponents are all like the anomalous dimension. You know, in the IC model it's a little bit strange. The anomalous dimension appears only at next to leading order. Here it's more consistent. Really, all the non-trivial information appears at next to leading order. The leading order doesn't give you any correction to the lambda out critical exponent. General remark. We will see this is a general fact. So somehow easing is special and ON is special. Then clearly we reproduce the known three critical exponents. So this is a double check that in all our steps we didn't go off the road. Now this is the discovery. This is the cool thing that we find out is that now the large n limit is non-trivial. And you see this is immediately because you see from these fractions that the power of n is the same numerator and denominator. This is in contrast with the standard ON model when we have n over n squared and q, okay? And yes, this is non-trivial. I think that there is a mistake there. And so you see that there is a non-trivial correction. So we go somewhere in the large n limit to a theory. And this theory has its own spectrum. So first of all, by just inspecting the spectrum, so the critical exponents, you've never seen them. I mean, there is not any other one. Now, actually, this calculation for the three critical case were made in the 80s or the 90s by doing the full calculations, and the work was done by Bardeen, Mosher, and Bander, and actually they discovered that probably it's really a line of fixed point in the large n. Okay, and then then there are various ways in which we can go much deeper in understanding the phase diagram at large n. For example, we could study the flow of the full potential, because here just one coupling is critical. But let's go on. Now we can do for the first time something that was never done, and is that we can just repeat the game at the theta critical order. Okay, so now we have the other block of functions, the one that have upper critical dimension 8/3. Okay, the leading order is free loop, and this is the expression for the leading order written down. Okay, and then now we try a potential with the mass and the coupling. Now it's lambda phi to the 8, so it's rho 4. We plug them inside. We exactly the same procedure. We just need now up to the vertex with 8 external V8, let's say I 8. The mega formula, la fantaziana mega formula is this one, okay, with all these contributions. This is 4 loops, 3 loops, and this other contribution of 3 loops, and this is also 3 loops. We put them inside, we turn around, and we get these expressions. Exactly like before, at the leading order you get only the contribution, this contribution here, and the next to leading order you get the one for the mass, and this other one proportional to lambda to the 3rd power. And we also get an expression for the anomalous dimension, okay, which starts to be interesting because you start seeing a pattern here. Yeah, where is it? N plus 2, N plus 4. And here is n plus 2, so you see that there is this pattern, no? and there is a coefficient in front, and then there is this pattern of n. The fixed point has this property, and it also goes to 0. But the critical exponents now, what happens to the critical exponent? Well, the critical exponent behave like the standard case, because now there is 1 power more in the denominator. So the tetracritical has a trivial large n limit. Okay, and so it seems the question is then only the tricritical that has this peculiarity. Then we can just go on and do this the next order. Now it's we have control over every criticality. So is there a pattern to be uncovered? So let's try the next order. So we go to the pentacritical. It now is this. Once you have written this one inside once in your life, then you apply to any theory you want. Okay, so we put this is the formula. So these are all the, you see this 8 loop contribution that comes inside, and you find the fixed point obviously, and you find these critical exponents. What is interesting is that now in this case the number of powers of n above and below is the same, so there is a non-trivial limit. And so you see that there is a non-trivial limit with these critical exponents. So we have this alternating behavior. So we have discovered that, so not only now let's try to imagine how is the theory space of one model. We have the criticalizing model, the critical model, the multi-criticals, and then their large n limit, some of them, the one which are, let's say, the three critical, the two critical, which is the standard one, the 4 critical, the 6 critical, the 8 critical, they all go to the Gaussian. But the other one, the 3 critical, the pentacritical, they all have a non-trivial large n limit, which is related to this Bardeen-Mosher-Bender fixed point. And so this is the beginning for really trying to elucidate all the properties of the UN model, because repeating the UN model, due to the Marmin-Wagner theorem, all the multi-critical models of the UN class do not show up as conformal field theory in 2 dimensions because of the Marmin-Wagner theorem. But they also have a variety of behaviors. But let's say it shows up in the large n limit. This is somehow the construction. So are these conformal field theories? Into what you can map it? So it's an interesting new thing that came out.
For the large n limit, which terms in the expression for the beta?
Yes, then this is exactly then how you do the analysis better. You redefine the coupling to have a meaningful large n limit, and you can look at that kind of arguments. Actually, you can look that there is a finite range of convergence, and this is the reason why actually, so there is an interplay between epsilon and n. So it seems that this is still to be understood actually, and there are some. So the idea is that you have. So this is 3 dimension, for example, and this is 4 dimension, and this is 2 dimension, okay? So, and this is n, and this is d. So the 3 critical fixed point is born around here, okay? Now, so basically, it seems that there is this line of fixed point is something that goes down up to a certain particular value. But now I will not have the time to explain and actually to review how it is. But yeah, you can look at the beta function and look for the it's clearly a balance of leading and next to leading order terms. So I think you are interested in that kind of. And we can have a look at that if you want. And the reason why I just show it from the spectrum, because the spectrum is universal. So the spectrum is there, and you just say, okay, let's see what happens to the spectrum.
So it has to be that the potential is odd.
Yeah. The potentials is. So we have so the 3 critical. So the standard one is this and doesn't have the large n limit. This one has a large n limit. This one doesn't have the large n limit. 3, no, this is a 4. This doesn't have, and this one has the large n limit, and the pattern will probably go on. We can check it. Okay, so this was a teaser. So this was one application, and where, let's say, is the first non-trivial application we can do from our general formalism, okay? And already at the level of the ON, there is something new. Okay, now what else can we do? So now we have seen the power of these master formulas, and now we can decide to study field theories in the most general way. And as we said, there are 2 general ways in which you can study. You can choose the symmetry and look for all theories with those symmetries. And this is what we're going to do now. And in particular, now we have looked at the spherical symmetry. So the spherical symmetry is the maximal symmetry for the field theory of the kind that we are considering. Now we can look at the symmetries of the objects that you can put inside the sphere, which are the interesting subgroups, actually the point groups. Because in principle we could look, so in principle a field theory, which is the fixed point of DRG, is a subgroup of ON. Of the subgroup of ON, there is these families which are the most interesting ones, which are the Platonic solids, if you want. And as you know very well, in 2 dimensions, we have an infinite number of regular objects, which are the polygons. Then there is the cubes of this one, 2 of them, the triangle and the square, generalized to any dimension. And they are actually what we call the symmetry of the Potts model and the symmetry of the cubic model, which are then families that we can treat as the ON model. So we have the ON model, which is the most general one. Then we have Potts models, which are like this, and hypercubic models. So these are the symmetries that are true for any number of fields. So these are the families, and to each one of these family, we can take the one in the critical. We have choices for the upper critical dimension. So here we choose 4. We could construct invariants in all these dimensions. Okay. Here we can construct invariants in the other family of dimension. Okay. And here we can construct invariants in this family. And so for each one of this, we have the same kind of analysis. We have the first dimension, which is normally has already been seen, which we can easily reproduce, but then we can immediately open up all their multi-critical versions. Okay. But then there is something interesting in the mathematics of regular object, and what is interesting is that for n equal 3 and n equal 4 are special because they have some additional symmetrical structures which are special to these 2 dimensions. And in n equal 3, they are the famous Platonic solids. And in particular, there is one special structure, which is the one that characterizes the symmetry of the icosahedron or of the dodecahedron. Okay, so the tetrahedron and the octahedron are one the dual to the other, so they have the same symmetry. So there is this object, and they have the tetrahedron is the S4, so it's the n equal 3 case of this, and then there is the cube and the octahedron. They are dual to each other, so they have the symmetry of the cube, which in the n equal case can be decomposed as S4 times zeta2. And then there is a new object, which is the symmetry of the 2 dual Platonic solids, icosahedron and dodecahedron. And so is this. So there is one real new stuff in n, which is the icosahedron field theory. And so now we can construct it. But to construct the icosahedron field theory, we need first of all to understand which are the possible upper critical dimensions to which we can look for, in which there is non-trivial RG information with this symmetry, and then we can look for fixed points. So what really becomes non-trivial now is the ability of constructing invariants. Because in the ON case, it was easy. We had row invariant, so we had row square, which were like 4 fields, so it's the critical 4. We had row 6, row 3. These are 6 fields, and this is the critical 3, and so on. Here, we cannot, in reality, we have also something in dimension 4. With Sn, the invariants are already more complicated. So how do you construct invariants? Because now it really becomes to the problem of constructing the invariants to know which are the upper critical dimension and to know which are the marginal potential to then put inside the master formulas. Then, when we go to n equal 4, there are 2 new additional objects. So there are the hypercubes, or the tesseract. There is the tetrahedron. This is the hypercube, tetrahedron, hypercube, and then there are these 2 new objects. Okay, the 24 cell and the 600 cell. So we have 2 icosahedrons in n equal 4, and then nothing more. So there are really these 3 special structures, so which we can ask, do they lead to some non-trivial field theory? Maybe yes, maybe not. So the idea is that, okay, now we can, in an easy way, study in full generality all of this in every possible upper critical dimension. What is interesting from the point of view of conformal field theory is that even if we will discover that the theory with the higher symmetries have upper critical dimension below 2. But they are the mother of some conformal field theory. And this could be some rational conformal field theory. Okay, but let's see how we do this in detail. And so here we need to put inside a little bit more of group theory. And actually this is a very nice part of mathematics if you do not know it. Because now we need to know, given a group, how many invariants with a certain field power can we construct? So let's take the group D3, which is the symmetry group of the triangle, okay? Which in this particular case is like S3, no? Fundamentally. It's not an easy problem, but the mathematicians have solved this problem. And the mathematicians they solved this problem in the form of something which is called the Molian series. The Molian series is a wonderful object that gives you, for your group, a Fourier representation. So we are looking at a two-dimensional representation of D3. It gives you a series. And the coefficient of this series have an important meaning because it tells you how many invariants there are with a certain field power. So this theory is telling you that there is one invariant with second power. So if there is one invariant with second power, so now let's make, how do I make the picture normally? Just a second. I'd like to make the picture. So let's say that this is n of the field power, and then this one is, and here we're going to put the number of this, then we put the invariants, and here we put the possible, the critical. So how do we see that? Okay, now let's look at this group. So we look at this series. There is one invariant with two fields, and we're going to call it E2. So there is one, and the invariant is E2, which is what we normally call rho. So it's the spherical symmetry. Clearly, this is the Gaussian theory. Now, what is interesting is that this is telling us that there is one invariant with three components. Sorry, this is n equal 2, and this is n equal 3. So there is a new object, I3, which I will call normally, which letter do I use in the example? Sigma, for example. And so the fact that there is an invariant with dimension, with three powers of the field, means that I can write down, let's write the group here. This is the table for the group D3, okay? It means that I can write the potential of the form, clearly, m squared rho, but then here I have G, okay, I can put 1 over 3, sigma. So let me for the moment just write symbolically, rho plus sigma, okay? So this is a theory that has marginal coupling here. So I can apply it, marginal coupling dimension. This is a dimension, I can use dimension, critical dimension 6, because this is 3 powers of the field. And so under the symmetry S3. Now we're going to, so there are two questions. One is to understand which are the possible invariants. Notice that the Molian series tell us how many they are. It doesn't tell us how to construct them. But to know which are in the logical, when we have a general symmetry, we need to know which are the possible upper critical dimension, which are compatible with the representation and with the symmetry. So now we know that there exists something with symmetry of the triangle and 2 components, so that we use our master formula for the critical 6 and we get something. And there will be 2 couplings in the marginal and relevant. Okay? Now let's go on. So here is telling us that, so another thing.
In this case, it can be just epsilon and j via.
Yeah, this is a little bit less trivial. We're going to construct it in a moment. Because then it become absolutely non-trivial, the invariance for. Let me stress another thing, is that this potential depends only on two fields, because it's n equal 2. So it's a v, phi, phi1, phi2. I can convert it in something that depends on 2. So it means that now that we're looking at 2-dimensional representation, there cannot be nothing new. So to be consistent now, if I look at the order 4, there is only one invariant. Yes, because the only invariant is rho square. If I look at the order 5, there is one invariant. Yes, is rho sigma. If I look at the order 6, there are 2 invariants. Exactly, because there is rho cube and sigma square. Okay? And then you go on like this. So you see that this is telling us that, okay, this is the master upper critical dimension for the Potts model. This is the Potts 3-state Potts model from the language of statistical mechanics. Clearly you can construct multi-critical, you can, okay, there is no meaning in constructing something with this symmetry in the critical 4, because this will be the leading coupling and this will just be a deformation. This will just be a deformation of the ON model. I can use dimension 10/3, which is this one, and have the marginal coupling which has this particular structure. And then in dimension, this is the dimension 3. Let's say this is not. There is something interesting because there will be the ON and a new operator which has this symmetry. And you can study, okay? So the Molean series immediately tell us, given a symmetry, where we can find something non-trivial. So now let's look at some other examples. So, and in this way I construct this column here, okay? And this is important because this is even before we go explicitly in the construction of the invariant. Now, if you look at the symmetry of the square, so you see the symmetry of the square have a different Molean series, because the symmetry of the square, we have n, the invariance, and here we put dc. And now we're looking at this thing here. So clearly this one we have rho, which is formally the Gaussian. There is no thing at 3. So this cannot, there is no 3 now. But there is 2 T4. So there is, at order 4, there is rho square and an I4, which is our sigma. Okay, so you see that now the potential is rho and sigma is something that has 4 power. So the critical is the critical 4, is the classical, is the main of the critical dimension for cubic symmetry. And in fact, it's one of the main symmetries used and its deformation in statistics for the approaches. Now you go, let's say, for example, let's go to the symmetries of the 5. So now you see that you have rho square, and you have a new invariant with 5 fields. And this is the invariant that encodes the symmetry of the pentagon. So this is a theory that exists slightly above 3 dimensions, which has a consistent RG theory that you can study. And then you can go on like this. And so you understand where a given symmetry or a given polygon has a field theory. Now let's look at the most the 3-dimensional representations. So if you look at the 3-dimensional representation, you see that this is S4. S4 is the symmetries of the tetrahedron. So now we get S4, and we have n equal 3. So the potential rho, sigma, and tau will depend on 3 independent invariants. And we have n, we have the invariants, and we have the critical, which are, so with 2 we have rho, okay, with 2 we have 1, which is our rho, and dimension is this one. Data. This is our full screen. So there is one invariant 3. So there is an sigma equal I3. So there is upper dimension critical 6. It's interesting. You see, there is an invariant. There are 2 invariants with 4. So there is rho square and tau equals to some I4. So now there is a theory even in the critical 4. And in fact, in the critical 4 you have both the 2 main deformations, or lesser symmetry, the one, or both the one with S, with tetrahedral symmetry and in cubic symmetry. Yes. You see, it's already different because in 3 there was not there. So if you want, this is we saw this is S3 and this is S4, and you see that there is a difference here. And so so you have tetrahedral symmetry in the critical 4. That's the reason why it was one of the things that has been studied a lot, because basically all the literature, the beta function in the literature, they come from only this application of the master formula, and sometimes of this. But then let's see so now we have all our 3 invariants. But for example, let's see, it tells us there is one of order 5. And yeah, the one of order 5 is the product of these 2. Okay? At order 6, we have 3 invariants at order 6. Which are they? So it's rho cube. Then there is, we are 6, sigma square. And then there is rho tau. Okay. And so if I want to construct theories with these things, in principle they are there, and you can go on. And and so, but let's say that the 2 main candidates, then you can decide, because until you put inside all the operators which are consistent with the symmetry, you're somehow looking at the basic theory. When you start to look at operators which are products of the invariants, they start to be somehow they are multi-critical versions. So somehow the upper critical dimensions, where you have the leading theories, the leading fixed points, are the one that allow you to have the non-trivial one that allows you to switch on all the invariants. So normally you say that somehow this is the line of the standard theory and these are the line of the multi-critical versions. You can study all of them, but that's the reason why I write 6 and 4 here. And then this is, now the key question is, okay, let's see the other 2 cases. So you see that now for a cubic theory, we have one invariant at the critical 4. So the theory can exist in the critical 4. And then you have there is a new one, because there is the cube of this one, but the product of this one is of order 5, okay? So this is this is order 4. The product of this one and this one gives 1. The product of 3 of this one gives the other one, but there is a third invariant, so there is another one. So here we have found, the color is that the first invariant. Now here we have one non-trivial invariant, because this is the rho is always present. So once I found the 2 non-trivial invariants, I've finished. Let's look at the icosahedral symmetry, which is the new thing. And here we have the critical. So the icosahedral symmetry, we have 2, we have rho. Then in 3, we have nothing. And then we have, in 4, we have only rho square. So we have nothing because it's just the ON. There is nothing new. And then with the 5, we don't have an invariant. So the first non-trivial stuff that is able to represent the icosahedral symmetry is at 6, because we have rho cube and our sigma, which is some I6. So this means that I can consider the theory in 3. So the first non-trivial upper critical dimension for icosahedral symmetry is 3. So this is telling us that there is no fixed point with icosahedral symmetry in 3 dimensions, because it's Gaussian there. So if there is something interesting with icosahedral symmetry, it's in 2. Okay, because it has upper critical dimension. So this is something that depends on 3 invariants, rho, sigma, and tau. Let's see where is the tau in the column. The tau, so if at order 7 there is nothing, but at order 8 we have 2 invariants, which is rho 4. But now, rho 4. I think I made a mistake. This is order 6, and then we have rho sigma. Okay, so this is, you can do it in 8/3. But what is interesting is that it's in 10 dimension, that in 10 powers of the field that we get the opening of the channel, because now we have this operator, and then there is another one because it's a 3. Here I made a mistake in the color. The coloring is there, which is tau. So this is to represent non-trivially the full icosahedral symmetry with 3 components. I have up to 10 fields, and I will show you how this thing looks like. Okay, so this is the way of first step, because when symmetry is complicated, you need to understand which are the upper critical dimension and which are the type of potentials that you can do. And you can do a lot of this analysis by group theory, because since now we don't need to do any more RG calculations, because we have the master formula for every symmetry. All our work will be basically related to representation theory and the construction of invariants. So first of all, we need to know where we can find invariants, to know which formula we need to use. Okay, and then we need to construct the invariants. So how do we construct the invariants? Now the reason why we selected this class of groups, because what we did up to now, we can just do it with any list of groups. You want to take the list of finite groups, you want to take the atlas of finite groups, whatever, and you can do the Molian series, and you can say, okay, where do I find a theory with the monster group symmetry? Where do I find the theory with a certain thing? No? You can somehow, but then the problem is, how do I construct these invariants? For these Platonic field theories, because this is how they are called, it's easy because they are symmetries of an object. And let's do the example of S3, D3, which is our triangle. Okay, so we have triangle. Let me draw it. Let me draw it in this way. Okay. So what we do is to draw these vectors, which are the versors to the vertices. So these are the 3 vertices. Okay, so this one is E. I'm going to call it E alpha equal to 1. Okay, so this is a vector which could be normalized or not. It's not really important. And for example, in our case, this is equal to 1, 0. Okay, and then the other one now we do. So then we just construct these quantities. Okay, and in particular, what I want to say is that one invariance, which I write there, order k, can be constructed by taking these combinations I1 to Ik and contracted with my fields. Okay? Now, if and these things here now I write them as E alpha II as the product of these versors and sum over alpha. Okay? So now these things is going to be invariant under the group of the object, because it's basically you can reshuffle the vertices as you want. So let's see. Here I made a little example. So as we said, this is A1. This one I call it E2, and it's equal to clearly plus 1/2 and square root of 3 over 2. And this one is what I call E3, and is equal to minus 1/2. Okay. So now what we do is to, for example, write the first invariant E2, and this invariant is the sum over alpha of E, so EI alpha. Okay, now they are components, so I don't need to write that, alpha, and then phi I, phi j, okay. So this can clearly be written as E alpha vector dot phi vector square, and so it's just E1 dot phi plus E2 dot phi plus E3 dot phi square. So the product of each one of this. So this is this. So what is one of this is very simple. So E1 is was 1, 0. So this is phi 1 square. And then what is this one? Okay, this one is the first thing. So it's sorry, I made a mistake here. This is a minus is here and the minus is here. Okay. So here we just do. We need to make the square of the scalar product. The scalar product is minus 1/2 the component plus square root of 3 over 2 the second component square plus minus 1/2 the first component minus square root of 2 over 2. Okay. So that's it. So you see now I put it inside and I just do the expansion, and you see that this thing here, if you want, is 3 times rho. Okay, where rho is the thing. Okay, so now we know that for every k we generate one invariant, but now we expect to satisfy that we know that there are only 2 independent invariants. So let's see that actually this thing turns out to be that way. Now the sigma will be the one with the sigma. We know that when we made the map before, no? In the Molean series, we know that there is one invariant with 3. So the invariant with 3 should come out non-trivial. And it comes out non-trivial. And so you see, this is the non-trivial structure of the S3 symmetry when you have a representation with 2 fields. But then what happens to the other invariants? For example, now I know there are no more invariants because this is 2 components and we already know that. So, for example, we compute the next one, the E4, and you see the E4 is, what is it doing? Okay. Okay, E4 is just rho square. Okay, this is the outcome. Consistent with the table that we made before, because we know that there is only one invariant at the order 4, and this can only be the order 2 invariant at the second power. And so you see it's exactly that. But now let's look what happens at the order 5. So at the order 5, we have only one u, and so it can only be the multiplication of this one with this one. And so you see that is exactly like that. And let's see now the order 6. So the order 6 is this expression. So the order 6 is more complicated, okay? But because in this case, so here we know that the order 6 there are only two invariants, and we know that is the square of this and the cube of this. But our invariants defined geometrically, at first sight, it doesn't seem the same. But what is important is that in fact, I can, and so let me call this one tau for a moment, okay? So then I look if tau can be expressed as a combination of sigma 3 and sigma 2 and rho 3, because this is what the Molian series is telling me, okay? So I do this, I get a system of equations. So for example, I set to 0 some of these components. And you see that there is a solution with, I don't know why here the numbers are different in this run, but okay, I want to have it, there is an 11, what happened? Okay, but what turns out is that yes, you can express.
I think alpha is type.
Ah, sì, sì, perfetto, eccolo qua, non è il problema. No. Let me multiply by 32. Divide by 32, just to make it more obvious, and then divide by 11 by 3. Ah, okay, okay. So you see that this 11, 15, 45, 9 is our tau, okay? So this is to show that, okay, now we can navigate through the complexity of the invariants because we know how many they are, at which order we should find. Then we have some generic expression for invariants for every geometric object. But these IK, they do not need to be all independent and so on. What we discover is that, I mean, you could do it blindly. You could just look at all these invariants and then look for a relation between them. But sometimes you will find them, sometimes you will not find them. So the rationale behind that is already done by the Molian series, which organizes all your computations, okay? So then we learn how to do the invariants. And now, for example, you can do this for the dodecahedron. And these are the three invariants. So if you remember before, we saw that the dodecahedron had an invariance which is O2 invariant, one invariance with 6 fields, and one which was the tau which was with 10 fields. So now we know how we do this procedure. You just take the coordinates of the icosahedron, tabled in every geometry books. And so you have these numbers, do those kind of things, and these are your things. And you know they are all your things. So you see that it's not really intuitive, the structure of the symmetries. And if you don't have a nice understanding of the group theory part, you get easily tricked. But now we know that we can construct a non-trivial theory in 3 dimensions by using this leading marginal coupling, or one even in 8/3, we're using this marginal coupling. And now we have all the formulas. So we just need to write the potential like a sum of certain couplings. So let's see an example. So now we can do the beta functions. So now we know that our symmetry has their invariant that we just constructed. We know that this is a 3rd order invariant. So we naturally studied in 6 dimensions with a marginal coupling, which is we call it X. Now we plug this thing inside the master formulas, okay? We have a code in Mathematica like before, and we project out the marginal coupling in the anomalous dimension, and we solve for it, and if we have positive eta, a real fixed point, we say that there is a non-trivial universality class. And in this case, this is the three-state Potts model around the critical 6. Now we can do the same for a non-trivial case, something new. For example, for the icosahedron, as I told you, there are 3 special theories, and this is the icosahedral theory. So the first non-trivial theory is the one with the critical 3, the one where the invariant tau plays a role. And there is also, so the invariant tau is the deformation of the rho, the spherical model. So you project this one, you have the anomalous dimension. So this system exhibits no other real fixed point apart the 3 critical O3. So it means that this is really just a deformation of O3. So in the critical 3, so only using one of the invariants which are specific with the icosahedron, it doesn't have enough strength to generate a truly independent fixed point. This happens also in the 8/3 case, where we could construct a theory using only rho and tau. But we know that icosahedron symmetry is fully expressed when we also have the third invariance, which is the one that we call the sigma here, I think. This last one, okay? So it's only when we use both of them, and so we are forced to work in 5/3, so that we are forced to use this page of beta function, this one, okay, which is an 8-loop calculation. We are able to find a system of beta function with this marginal coupling that has real icosahedral symmetry. And there are actually 2 fixed points. So there are 2 non-trivial CFTs with icosahedral symmetry that have upper critical dimension 5/2.5, so that they must go in 2 dimensions to something. And so in 2 dimensions, we expect 2 theories with icosahedral symmetries. And then you can also compute their things. So you see, this is something that we were able to do with that because of our different approach to the beta functions that goes through. And with a clear factor in mind that RG calculation and symmetry is completely factor in the epsilon expansion. You don't need to do any new RG calculation because we did all of them in a very systematic way. Now we just do look at the group theory part, which dictates the structure invariance, which dictates which upper critical dimension we use, which dictate which master functional we use, which allow us to deduce the beta function without doing any loop computation at all. Okay, so then we can do this systematically, because now we can add a new line, a new column to the group theory table. So we have our Platonic solids so these are the 3 non-trivial dimensions. With the reasoning of the Mollian series, we list the upper critical dimensions which are candidate, and in general we list those which we call here are the standard one. So all those upper critical dimensions until which all the possible invariants are switched on. And we have seen that for the icosahedron this was key, because it was only when all of 3 the invariants were on that we found true icosahedron fixed points. And so you see here, and then if you look for fixed point, this is our system of algebraic equations. There are more than one marginal coupling, so sometimes there is no real fixed point. Sometimes there are fixed points with higher symmetry, so only the O4, or sometimes there is the cubic one, okay? And so here we match all the fixed points. Okay, so this way we have systematically studied what are called Platonic field theories. And most of them, they have upper critical dimension below 2. So most of them will be actually really interesting when they go in 2 dimensions, because they are some non-trivial conformal field theory. And then for each one of them, we listed here all the critical exponents in the epsilon expansion. And then you can look in the deformation. So you can do really everything. Okay? So we did a very systematic study driven by symmetry. We have chosen a general family of symmetry, and we studied all the theories with that symmetry. So now you can do this for any kind of things, You can take the table of groups. You can have the theory coming from your project, whatever it is, and you can really study the things. Okay, and then, as we said, so these were the specific cases, the cases with 3 components and 4 components. With 5 components or above, we have only the Potts family, okay, that we have seen in the specific case. Also here we can write down functional expressions. So we have seen that there are 2 invariants, which are this one. So now our functional u will depend on tau and rho, and so our beta functions will become partial differential equations. This could be studied at the level of the partial differential equation or can be used to reproduce the beta functions. The new theory that we studied in this paper was the theory with SN symmetry, but in 10/3, because SN symmetry apart n equal 4 can be realized only in odd dimension, okay? And the invariants are constructed with the same logic. And now we have to use this new beta functional that were not known before, because they are the generalization of this one in 10/3. We find a non-trivial set. Now it's interesting because there are 2 non-marginal couplings. So the space of fixed points becomes more interesting. We said that this is consistent with an annihilation scenario of the Potts model, the fact that it's first order in 3 dimensions. But here we are more interested in percolation and correlated percolation and things like that. And now to conclude, we did also work where we did the same analysis for the cubic model, because the other family which exists for every n is the cubic model. And so here there is also multicriticality, and again the physics of this multicriticality is very interesting. So going back, Platonic field theories means all field theories that have the symmetries of a regular polyhedra in a certain n. N will be the representation of your, in a certain dimension n, and so there are the Potts family and the multicritical Potts, the cubic family and the multicritical cubic, and then there are these 3 special cases. And these 3 special cases, we have seen here that the icosahedral symmetry special case exists when we have all the invariants inside, and the same thing happens with the 4th cell, with the 2 special cases that we have in 4 dimension, that you need to go to have a lot of symmetry to see some fixed points, because you really need to put inside all the invariants that characterize this symmetry. And while for the 600 cell, which is the other, we didn't find. We didn't find it. So there is none. And that's it. Yeah, okay. So
because you have 2 fixed points, is because
because you have more, because you have a system of you have more couplings. So when you have more couplings, it's like, for example, there are various fixed points and with a certain flow between them. Because now you have, with general n, you can, for example, here, you see here you can have more fixed points because you have 2 couplings with 2 couplings and cubic interactions. So, and actually, and so basically now, whatever group you want to study, whatever symmetry, you can impose it and go directly all the way down to the physics. What time is it? Okay. Yeah.
You can only flow to one of the 2, right? So it must be that it's a combination of.
Yeah, you can.
I've chosen a basic beta function that was mixed.
No. Then you find. So the point is that you find all the flow. The flow will have some fixed points. One will be more attractive. Then you can decide that you want only the maximal attractive one. But if you just want to plot the phase diagram has these fixed points, and then you can plot the flow. Really, draw it. And there are 3 couplings. It's a 3-dimensional flow. You can look at all the formation, and so for each one of these entries, you have the flow. and you can combine them. Here we just listed the fixed points because it's like the first thing you want to do, to see which classes and to do systematically this kind of analysis. Okay, and then to conclude, this is a place where we decided that we give the symmetry. But now we can do even something more general. We just look at the most general theory with a certain number of couplings, with a certain number of components. And so this opens another scenario, which is the one under which we are also working at the moment. Okay, I think I'm going to stop here. Bien. If you have any other questions, otherwise we...
Yeah, the Lagrangian is a field phi, right, with one index. But that index doesn't have to be ON index, right?
Yes.
It can be like in the adjoint of some group. And then the potential, if you think about matrices, is built out of traces or commutator, which is...
Exactly. All this can be, these master formulas can be extended to all these cases. So we didn't do it, I didn't do it, but from these formulas you can do the same thing for matrix, if your order parameter is a matrix or is a tensor. I think that everything can be deduced from this kind of structure. Somebody did it, they use it for doing B fundamental or 3 fundamental theories, whether it's ON times ON times ON.
Yeah.
There are, I mean, you can really do whatever you want. And even other kind of indices. I think that most of the things will go through and you can just transform them. So this relation are even much more important. What is really key, that I repeat, is that the RG part in the Epsilon-Expansion are just these coefficients that we saw in the one component case. So when you go back to this table that we constructed by various arguments in the first days, these are all the numbers that you need to know. You see, because the coefficients here and here, and then they will generalize to the multi-component case. So once you have all these numbers, you have the map, and then you can basically study a lot of...
But when you have matrices, you might have... so if you have U1 or U2, don't you also have... is it always true that the reduction to one component works? Like if you
No, it may not be true. It may be that you have only a constraint. Or it may be true that it works only a leading order and not an next to leading order. Something like that. And one has to explore it. But just keep in mind this possibility, that you don't have to do ex novo your computations, but most information can be extracted from simpler calculations already available. Because sometimes even just working functionally, if somebody has computed a beta function, you can infer the coefficients from the beta function, and then from the beta function derive all the other beta functions. Because the beta functions, they're not all independent like we generally think. So you can play all these games. And bien, well, this is all for today. Then I will stop here. Bene, andiamo a bere un caffè?
yes.
So you have to go to your meeting?
Yes,